Iron has a specific heat of 460 joules per kilogram Kelvin. Gold has a specific heat of 130 joules per kilogram Kelvin. A 200-gram gold bar at 300 Kelvin is put in contact with a 400-gram iron rod at 500 Kelvin and allowed to come to equilibrium. What temperature do they wind up at in equilibrium? So this is a calorimetry situation, although it's maybe a little bit different than like a lab technique type of calorimetry situation. In that type of a situation, more likely you'd actually measure the temperature that the system or the combined system winds up in equilibrium, and then you would use that to calculate one of the specific heats based on the other one being known. So that's more of an application there. But this, nevertheless, this question is of a similar type and will give us some idea of how to analyze calorimetry type of setup. So the key concepts page said, I think it said Q heating was equal to minus Q cooling, but it might be simpler to just say that Q in is equal to minus Q out. Oops. Let me make that it's supposed to start with the letter O, right? Not U. I want to draw a picture of this scenario to help me kind of figure out how to get all the parts into place to use this as kind of a starting point for my analysis. So what I'm going to do is I'm going to draw an object here that might represent, what was it? It was a gold bar, I guess, right? So this can represent the gold. I put in contact with a iron rod, which I'm just going to draw like a piece of iron underneath here. Just assume that it's a rod, right? And the iron is starting at 500 Kelvin and the gold is starting at 300 Kelvin. So 300 Kelvin is pretty close to room temperature. In that sense, it's the iron rod that is hot, and the gold bar, of course, is being heated by the transfer of heat coming from the iron and going into the gold. So I want to draw in my picture here an arrow and then maybe label it with a Q to say that's, at least at a conceptual level, what is going on. I think for later reference, I'm going to state that the temperature, the initial temperature of the iron, I think I'm just going to say T sub Fe, because that's kind of the chemical symbol. If you wanted to use T sub I for iron, that would be fine. Whatever you want to do is fine. But I'm just going to state that as 500 Kelvin, and that's going to be the initial temperature of the iron rod for this problem. And then I'm going to say T, I think for gold it's AU if you want to go with chemical symbols, which I've decided might be cool and interesting. But again, anyone can do different subscripts, right? So if you're not as into chemical, like periodic table type of abbreviations for elements, you might do it differently. Maybe put G for gold, right? But those are the initial temperatures, and I'm going to refer to them later. And in turn, we also have that the mass of the iron rod is 400 grams, so maybe that'll be 0.4 kilograms, and the mass of the gold bar is 200 grams, so that's equal to 0.2 kilograms. And then we're given the specific heat. So I'm going to associate symbols with all of these in what I hope is a sensible way. So the specific heat of iron is 460 joules per kilogram Kelvin. Now we're going to see that this, as a math problem, this one is maybe on the horrendous side. And so I might want to drop some of these units and just make sure that all my units, I've kind of already standardized, right, to kilograms for the two mass quantities. And I think I'm just going to, again, drop those there and not worry about unit balancing. It'll probably be obvious that it works out, I think, when we look at it later, but just because there's not going to be enough space to write everything I need to, which I might get in trouble already with that, given how much space I've already used. But let's see, we got 130 joules per kilogram Kelvin for the specific heat of gold, and this might be enough information for me to start this out. So when I say Q in, I think that it's clear from the picture that the heat is transferring into the gold. So if you remember that formula that I shared from the specific heat topic, Q is equal to C times M times delta T. So Q in, I could say, is, since that's for the gold, we'll say that that's C AU times M AU. And then I'll just write here delta T AU is equal to minus, now the heat is coming out of the iron, right? So this is all going to be iron quantities or iron related. In other words, specific heat of iron, mass of iron, temperature change of iron. And so that's kind of my first step, is just using that formula that relates heat to specific heat, mass, and temperature change. And now I might like to, I'm going to have to start over here to give myself a little bit of space, I think, because I want to think about like what are these temperature changes really going to be in terms of some other symbols. And then pretty quickly I'd like to start just putting some numbers into this, because symbols, too many of them get scary. But the delta T for the gold is going to be T minus T AU, at least if I assume that this T without a subscript really represents the final equilibrium temperature. And then on this side, I'll do kind of a similar thing. And notice I've tracked through this minus sign, because it turns out if I'm very careful about this with that minus sign, that will make this all work. So this one will be T minus the temperature, the initial temperature really of the iron, which is what we call TFE. So this is kind of my setup where I've used subscripts and symbols to kind of conceptually track everything that I'm doing, starting from this original principle that gave me, again, a starting point for the problem. But at this point, I might already be ready to plug in the appropriate numbers for this. But again, I'm not going to have space for units. So I'm just going to say CAU was 130 specific heat of gold in standard units. The mass of the AU was, let's see, 0.2. So I'm just going to put that in kilograms, but again, I'm not writing the kilograms. So we're just assuming everything is in correct units. If you look at it, the specific heat times mass kind of balances on both sides. The temperature, of course, T is the thing I'm trying to solve for, and the initial temperature of the gold is 300 in Kelvin, but I'll just assume that we're going to get something out in Kelvin, and I think that makes sense, because when you look at these numbers here and their units, in particular, basically the specific heat units, the mass units cancel, and you've got temperature equals temperature. So we'll get an answer in kelvins, therefore. And this one's going to be T minus 500 there. And, oh, I made a little mistake. Does anyone see what my mistake is? I'm going to fix it now. I was talking too much and did not catch. I wrote the wrong mass in here. This should have been 0.4. So let me go ahead and fix that. That maybe illustrates, I mean, it's good to have a beginning, but there's lots of little details, and I have to use these subscripts. It's really easy to get confused. So it's good to sometimes go through and double check your step, or look and say, okay, wait a minute, does everything make sense? Because one mistake and your answer won't be correct. And it's one of the reasons that in this class we often do focus on process and showing step, because that makes it easy to identify where the mistake happened. Whereas if you just look at a final answer, nobody really knows what happened. It can be very, very mysterious. And that tends to be true in like real life type of situations as well, where calculation is involved. So, okay, that I've got a lot of space there. Maybe I could do it, but that does look kind of like a horrendous math problem. I might not even have enough space to really do it, but what I think I can say is if you do a bunch of algebra with these numbers here and you isolate t, the expression that you get, I'm kind of looking at like if I were to kind of like maybe multiply this by these factors, then add it to the other side, and then maybe take the 300 with these numbers and add that to the other side, and then from there I'd be able to like kind of sum and divide, etc. But what you wind up getting from that, I don't know if I have the words to describe it really, but if you part of that is going to wind up being 460 times 0.4 times 500. That part actually came from these three being multiplied and then summed with 130 times 0.2 times 300. And then when you look at the part that sums together with the isolated t, I'm going to divide by all of that, and that'll wind up being, let's see, 460 times 0.4 plus 130 times 0.2, and really that part actually came from right there, and this part kind of came from right there that was added to the other side when then it was all divided off. Actually, what's interesting about this is I kind of wrote it this way deliberately, and again, I skipped some of the algebra steps because I really, even though I still have a bunch of space left over, I really don't think I could have done it in the space that was there. But what's interesting about this is this looks kind of like a weighted average of the two temperatures. It's kind of like I just averaged the two temperatures weighted by the specific heat multiplied by the amount of mass of the substance that was there. And I can put all of this into my calculator. My calculator says 475.2380952, but I think under the circumstances, maybe it's okay if I round that off to 475, and that should be in Kelvin, and that's actually going to be my final answer right there. So again, I skipped some of the algebra. If you want to get your own sheet of paper and mess around with the algebra from this equation to get to here, feel free to do that. Or if you trust my algebra, that's maybe okay. Or if you don't trust my algebra, let's check what the slide says. And there it is. It does eventually get to 475 Kelvin. And notice here that it did the subscripts. This is pretty similar to what I had on this line, kind of my third line right here, but the subscripts were done differently to kind of illustrate that there are different ways of doing it.